14.7. Flow of viscous fluids in pipes. The outline of this video is as follows. We will begin by moving beyond the concept of an ideal fluid to discuss the behavior of real fluids, which have internal friction. We will then build an analogy between the equations governing fluid flow and other transport equations in physics, such as those for electrical current or heat transfer, to see a unifying pattern. Next, we will formally introduce and define viscosity, the key property that quantifies a fluid's resistance to flow. Using this concept, we will then derive Poiseuille's law, which is a fundamental equation for calculating the volume flow rate of a viscous fluid through a cylindrical pipe. Finally, we will explore the powerful implications of this law by applying it to the human circulatory system, explaining the physics behind blood pressure and flow. We will now explore the behavior of real fluids, which differ from ideal fluids because they experience an internal friction called viscosity. Let us recall what we learned about ideal fluids. According to Bernoulli's principle, if an ideal fluid were flowing at a constant speed in a uniform horizontal pipe, no pressure difference would be needed to keep it moving. However, this is not what we observe in the real world. In any real system, a pressure difference is required to maintain a constant flow rate. This discrepancy is due to the property of viscosity, which is a measure of a fluid's resistance to flow. You can think of it as internal friction between adjacent layers of the fluid as they slide past one another. Our own circulatory system provides a perfect example. If blood were an ideal fluid, the heart would not need to pump continuously. Because blood is viscous, the heart must always work to create a pressure difference that overcomes the resistive forces in our arteries and veins. Therefore, for any real fluid, a continuous pressure difference is necessary to overcome internal friction and sustain flow. To understand the flow of real fluids, we need a relationship that connects the driving pressure, the resulting flow, and the opposition to that flow. Unlike ideal fluids, real fluids require a constant push to overcome internal friction, which we call viscosity. The equation that governs this is delta P equals I sub V times R. In this formula, delta P is the pressure differential between 2 points in the pipe, which acts as the driving force. The term I sub V represents the volume flow rate, telling us how much fluid moves through the pipe per unit time, for example, in cubic meters per second. The final term, R, is the resistance, which quantifies how much the system opposes the fluid's movement. For instance, to push water through a long, narrow garden hose, you need a greater pressure difference than for a short, wide one, because the long, narrow hose has a higher resistance. The essential idea is that the required pressure push is proportional to both the flow rate and the resistance. The equation for fluid flow is a powerful example of a general concept in physics, known as a transport equation. Understanding this pattern allows us to see deep connections between different physical phenomena. The basic structure of these equations is that a driving influence causes a flow, and this flow is impeded by a resistance. For fluid flow, a pressure difference, delta P, drives a volume flow rate, which we call I sub V, against the fluid resistance, R. This is directly analogous to Ohm's law in electricity. In a circuit, an electric potential difference, delta V, drives a flow of charge, which we call current, I, against the electrical resistance, R. The equation, delta V equals I times R, has the exact same mathematical form. We can even see this pattern in mechanics. A net force is the influence that causes an object's acceleration, A, which can be thought of as the resulting flow of motion. The resistance to this change in motion is the object's mass, m. This general principle of an influence causing a flow against a resistance applies throughout physics, including to heat transfer, where A temperature difference drives the flow of thermal energy. Let us explore where the resistance to fluid flow actually comes from. The key concept is viscosity, which is essentially the internal friction within a fluid, and the reason we need a pressure difference to maintain flow. This friction has two main sources. First, a resistive force exists between the fluid and the inner walls of the pipe it is flowing through. You can think of this as the fluid sticking to the pipe surface. Second, and just as important, there are resistive forces between adjacent layers of the fluid itself. Because the fluid at the walls is nearly stationary while the fluid in the center moves fastest, these layers must slide past one another, creating internal friction. We can model this behavior by looking at how a fluid deforms under a shear force, as we will see in a moment. For example, honey is much more viscous than water, and this high internal friction is why it flows so slowly. In summary, viscosity is the property that describes a fluid's resistance to flow, caused by friction at the pipe walls and between the fluid's own layers. Let us now formally define viscosity, which is the measure of a fluid's internal friction or resistance to flow. Consider a layer of fluid of area A and thickness, h, to move the top surface at a speed, v, while the bottom is stationary. A shear force F is required. This force is proportional to the area and the speed, and inversely proportional to the thickness. We introduce a constant of proportionality, called viscosity, and denoted by the Greek letter eta, to create an equation. The resulting formula is the force F equals eta times A times V, all divided by H. This means fluids with high viscosity, like honey, resist flow and are considered thick. Conversely, fluids with low viscosity, like air, flow easily and are considered thin. The standard unit for viscosity is the Pascal second. A common alternative unit is the poise, where 1 Pascal second equals 10 poise. Therefore, viscosity is the property that quantifies how much force is needed to make a fluid flow at a given rate. Now that we have a formal definition of viscosity, let us look at some real-world values to get a feel for what this property means. This table shows the viscosity for several common fluids, measured in units of millipascal seconds. The most striking thing is the enormous range of these values. Notice how the numbers span over 7 orders of magnitude, from air at the low end to peanut butter at the high end. Air has a very low viscosity, which is why we move through it with almost no noticeable resistance. Water is more viscous but still flows easily. In contrast, honey has a viscosity thousands of times greater than water. This high internal friction is why honey pours so slowly. This property is precisely what causes the parabolic flow profile in a pipe that we saw earlier. A fluid with higher viscosity will have a more pronounced difference between the flow speed at the center and the speed near the walls. Ultimately, viscosity is a single numerical value that quantifies how thick a fluid is, or how much it resists flowing and deforming. Now we can combine our general pressure-flow relationship with the specific factors that determine resistance. This leads to a very important result known as Poiseuille's law, which quantitatively describes viscous fluid flow in a pipe. The resistance, R, of a fluid flowing through a pipe depends directly on the fluid's viscosity, which is represented by the Greek letter eta, and the length of the pipe, L. The formula is R equals the quantity 8 times eta times L, all divided by the quantity pi times R to the 4th power. If we substitute this expression for R back into our earlier equation, delta P equals I sub V times R, we arrive at Poiseuille's law. This law states that the pressure difference, delta P, is equal to the fraction 8 times eta times L over pi times R to the 4th, all multiplied by the volume flow rate, I sub V. The most critical part of this equation is the radius, R, raised to the fourth power in the denominator. For example, if the radius of a blood vessel decreases by half, the pressure difference needed to maintain the same blood flow must increase by a factor of 16. Poiseuille's law provides a complete description of how pressure, flow rate, fluid viscosity, and pipe dimensions are interconnected for smooth, laminar flow. Poiseuille's law reveals a crucial relationship between the pressure difference needed to move a fluid and the radius of the pipe it flows through. The most important takeaway from the equation is that the pressure difference is inversely proportional to the radius raised to the fourth power. This means that even a small change in the pipe's radius has a very large effect on the pressure required to maintain the same flow rate. For example, let us consider what happens if a pipe's radius is reduced by half. Because of this fourth power relationship, the new pressure difference needed will be 2 to the power of 4, or 16 times larger than before. This is a dramatic increase for just a 50% reduction in radius. This principle has critical implications for our circulatory system. If an artery becomes narrowed by plaque, its effective radius decreases. To maintain the necessary blood flow, the heart must work substantially harder, leading to a dangerous increase in blood pressure. This powerful dependence highlights why arterial health is so important. Let us summarize the key relationships that govern the flow of real, viscous fluids. First, we have a general relationship for flow against resistance. The pressure drop, delta P, equals the volume flow rate, I sub V, multiplied by the resistance, R. The physical source of this resistance is the fluid's internal friction, which we quantify using a property called viscosity, or eta. When we apply these ideas to the common scenario of a fluid in a cylindrical pipe, we get Poiseuille's law. This equation combines all the factors: the fluid's viscosity, the pipe's length and radius, and the flow rate. The most important takeaway from this law is the powerful influence of the pipe's radius. Because the resistance is proportional to 1 over the radius to the fourth power, even a small decrease in radius requires a much larger pressure drop to keep the fluid moving at the same rate. To wrap up, let us apply our understanding of fluid dynamics with 2 review questions. The first question presents a biomedical scenario. A patient's artery radius is reduced by 10% due to plaque. Assuming the heart maintains the same pressure difference, by what percentage does the blood flow rate decrease? To solve this, use Poiseuille's law, focusing on the powerful dependence of flow rate on the radius to the fourth power. As the hint suggests, a good strategy is to set up a ratio of the new flow rate to the old one. This will allow the other terms to cancel out. The second question asks you to recall the analogy between fluid flow and electricity. We compared the equation delta P equals I sub V times R to Ohm's law, which is delta V equals I times R. What physical quantities in our fluid system correspond to the electric potential difference, delta V, and the electric current, I? Think about what provides the driving force in each case, and what quantity measures the flow itself. Please pause the video here and take a moment to work through these 2 problems.